Hello, Professor. I hope you are well. And this is our 4 and 5 term paper. And I'm Justin. On behalf of our team, I'm doing this recording for our term paper presentation. So this paper, firstly, I want to briefly introduce about our paper, what they have done. So they basically proposed a module, partially exchangeable networks. It is used to approximate the Bayes computation to show that their module is better than the existing modules. And so from the abstract, we can see that they're using the partially exchangeable networks, and it has some advantages that it is invariant to block switch transformations, and also this is also the case of the Markovian process, and also to compare within the partially exchangeable networks within the multi-layer perceptron. It introduced in the later part to show that their module provides more reliable posterior samples even when using less trained data. And so firstly, they are introduced about the approximate Bayes computation. Actually, it is kind of to using some parameters in the formula, and this formula using some the experimental data that is also known, and to predict the future data, and to compare with the predicted data and the real data to try to lower the difference between each data, so to get the parameters that could be used for the further prediction. Here is some the definition of the variables, like the proposals, the theta. This is also this is also like a matrix. Not, it's a vector because it's the multi dimensions, and also this is the estimated data by using the parameter, and also the y observed value means that this is the exact value. Y star means that this is estimated value. Okay, and the statistic means that in this paper, that means that the summation of the difference between each observed data and the proposed data. And also here they're using the mathematical formula to show how they calculate it. This is also very important for their code. And this is learning sample statistics. And also in this part they introduce that how to calculate that the parameters. And so from the literature they find the other team, they proposed the linear regression module, and they are basically using the least squares to calculate based on the data to calculate the parameters. And the kind of using the estimate data for one data, and since we have the multi-dimensional variables for each set of data, so they actually first using the one set of the data to estimate the linear regression, and then using that kind of many data, the vector, to predict the whole data set. And from the literature, they also other people also did that using the multi-layer perceptron regression module to replace this linear regression, and they are perform actually good. But in this paper, they actually using this partially exchangeable networks to replace the multi-layer perceptron to show that they have the better performance. And for here, they introduce why. It means exchangeable networks. It means that even we change the parameters here, the final results will not be affected. That's the exchangeability. And this also there's the mathematical proof induction to prove that it will not be effect. Okay. So for the partially exchangeable networks, they are defined by this PND, P of order D. This basically means that the D means the order of the partially exchangeable network. Means that the order of D means that the current value is affected by the previous Hamming value. If the order of 0, it means that the previous value is only affected by itself. Such as like this linear regression module, they are only concerned about itself. Okay, so that basically means that P order of 0. But for this paper, they also propose other modules like the moving average and autocorrelation. They are not only 0; they have many. And so here we come to the experiments. So they're basically using the 4 modules, 2 static modules, G and K and the alpha stable distributions, and the 2 time series module, autoregressive and the moving average. They are using the order of 2 of them. So this is kind of G and K distribution, and from their experiment, they showed that you can see when the dataset is kind of the 10 cube, okay, the difference between them, or say the data they predict whether it's precise, is same as kind of the lower than the multiple percent, but they don't have the big difference. And when the training data goes further, they have the better estimated value compared to the multiple perception. But for this, by using this G and K distribution, and they find that actually in the low data set they didn't have the very obviously better performance. And then they're using the alpha stable distribution. And for this, they propose some method that using multiple perception, small, large, and pre. And by using the PN0, this is they proposed. So from this we can see that by compare the root mean square error, they find that whatever the data set it is, they don't have the big variance. They're very low, like the 0.07. But using the multiple perception, they're kind of big, at least 0.4. But when the data set becomes very big, you can see the multiple perception pre is kind of the same as the proposed model PN0. So this also can show that the advantage of the proposed model, that it is very stable, very precise, and also using the small data set can achieve the very good performance. And so the next two, I will introduce the more precisely. This is autoregression time series module. By using this, also using the 5 lags. This means to -1, -2. This means -1, -2, but this means -2, -3, -4, -5, respectively. So for this module, I want to introduce that. The autoregression module is kind of like this. So this is a current value. So current value is dependent on the current value is dependent on the previous value, like this. If the function is like this, okay, not this. It is like this. So this value is dependent on this value and this value. This is t-2, t-1, and this t. So this is white noise. White noise means that the expectation, the mean value of it from this feature, they define it as 0, and the standard derivation is 1. So this is a white noise, because if there's no white noise, the function will become a line. Okay, so a picture for this, we can find that the lag, we calculate the expectation of this function. We can get that expectation. So we can get the lag. So we actually calculate the expectation of the YT. It is a lag. So this means a lag. They proposed this lag for the paper, but they didn't introduce this. So I want to briefly introduce about it here. Okay. So basically using the multi-large PN0, 2, and 0, because this is affected by the previous two values, so it's kind of the order of 2. So actually for this one, how they using the proposed this formula, this module to get the parameters. Actually, this can be a little bit tricky, and they didn't introduce this too much here. But I want to introduce here for the details. So basically, from the other module, this is lag as we introduced. This is the lag between them. You can see here. The lag, okay, lag I. So let's continue for the autocorrelation module. So here we have the formula like this. I like this, and this is white noise, and this is auto covariance. We can get the expectation of YT multiply YT minus 1. We can get this. And because here is a very important thing that because white noise and the Y value, of course, they do not make sense. So expectation of this it should be 0. So from here we can get because this is lag, this is minus 1, so we can get this is the autocorrelation covariance. This is minus 1, we can get here plus 1. So this is minus 2, we get there plus 2. So basically we have the autocovariance formula. We can simplify like this. And the fact here is that the autocovariance of 0, like here, it should be the square of the standard deviation. And also there is a fact that the autocovariance of k, it should be the autocovariance of the minus k. This will make sense, so because it's very intuitive. So autocorrelation here, we can find that if we divide both sides from this formula and this, we can get the autocorrelation formula like this. Okay, so from here let's continue. So let's consider because this makes sense. So autocorrelation in 1, 0 is 1. This will make sense. So itself the autocorrelation should be 1 because the function and with its own self, it should be 1. They are totally correlated. So if the minus 1 should also be 1. So this means that the autocorrelation between minus 1 and 1, they also should be the same. Like you move 1 here, 1 here, they will not affect the autocorrelation the numerical value. So here we can get the, suppose we suppose the k is equal to 1 and 2. We can get the autocovariance or autocorrelation formula for 1 is this, and P2 it is like this. So finally we combine to the matrix, we get this. So the amazing thing is that this can be like the function like x equal to matrix plus multiply b. So b is equal to the matrix minus 1 plus x. X is our data, and the matrix minus 1, it is this. So by calculating this, we can easily get the b value, the b1, b2. It is also the autocorrelation, autoregressive module for b1 and b2. It is also the value in this paper for theta 1 and theta 2. We can easily get this. Okay. So beside of this, we come to the moving average. So basically for the moving average, what this means, why are using this kind of white noise value? So basically I want to introduce also briefly up here. So for example, we have the series of the function like this. So let me suppose the standard deviation of this is equal to 2, and the mean value it is equal to 0.5, let's say. So this when time it is equal to t. So when time it is equal to t plus 1, the mean value is also should be the 0.5. The standard deviation is also to 2, because the 2 days data they will not change too much. So how to use these two kind of things to predict t plus 2? How to predict? And suppose we can suppose that the value here, the function here is at yesterday's value, and this is the day before yesterday's value. So we actually have to combine those kind of two to our new value, to our new function. So we basically add this to a function here. For example, the new function should be like the xt is equal to the ft plus kind of the variance here. So if there's no variance as promised, it should be the a straight line here. This is kind of we'll call it the white noise. So here, and the new function here, you can find that suppose this is the white noise 1, and this is the white noise 2. So the new proposed function is kind of like the combine these two. Those two white noise, that kind of the let's see, the xt plus 2 it should be equal to the theta 1 plus multiply wt and plus theta 2 multiply wt plus 1 and to plus some white noise value. So this white noise value basically means that also maybe some difference between this combine this, and we get we also make suppose this value and this value to combine, it should be like this, but the real value maybe some difference or upper and down, it will not matter. We just add the white noise value here. So this makes sense to here. So you can see the model here, we just to find the theta 1 and theta 2. Okay, so by using this or let's see, by using the autoregressive time series model can find by using the low volume of the dataset, we can have the very good performance by using especially for the PEN2, like to using the autoregressive time series module for for the order of 2. So you can have this. it is much performance is much better than the multi-layer perceptron, and even by using a large data set. Okay, and by using the moving average, we can find that for the moving average, the experiment like this. So their proposed module of order of 10. It means that for what? What this means? It means that plus theta 1, theta 2, theta 3, and extract for the theta 10. So they are using moving average of theta 10. Actually, there is also a trick thing that the moving average, infinite order of the moving average, it is autoregress time series 1. But this is it's like this. So the moving average infinite should equal to the autoregressive of order 1. This is very famous the fact that this should be the same. But I don't want to prove here, since this is not totally related to our today's topic. So by using moving average, you also can find the performance by using the order of 10. It is also by using a small data set, we can get the better performance compared to the multi-layer perceptron and the PEN0. Okay. So for the paper is is all of them. So basically for the paper, the most important thing is that by using the linear algebra and the mathematic the proof to calculate the rationale of the process. So for the code, we also find it we're using the Jupyter and the kind of using the Python, and you also can find the data is also in their directory. They have the full data. So for the code part, it's kind of simple because they only need to input the formula they have proposed. They just need to input those kind of formula and using the data to get the plots. So for the code, basically there is no kind of the technical part to explain. So we just to run this code. The code is also it is already run. So we can find this is for the auto regression plot posteriors. We can find using they input this formula to here. The alpha is 0.3 they proposed, and we can find this. And they just all of them just define the x label and the plot. This is from this x, the range of the x, and this is the range of the y. And so this is not the very hard part. So basically for each they have about 1, 2, 3, 4, 5. They have 5 code files. So each file is used to compare with the full experiment. So basically for each file, they just using the plot by using the data. You can see many of them. They are kind of the same. The same code is used to form the similar the graph. Okay. So this is for the RES. For this code is for this part. So for this one, alpha stable distribution. Okay, and they also run the code and they get the results like this. They put in the paper. So for this also don't have the technical part that using the for loop to plot a full graph. Okay, and for this is for using moving average too. So using the moving average too, the moving average too is about is here. Moving average too is the plot. So you can find that the step by step they finally get this result. So kind of so there also no technical the technical explanation here, and for this is for the using the distinction between the difference between them. So basically this is for the For which graph? This is for this graph for finding the G and K distribution. You find this. And for the AR2 plot here, we basically find the plot. Finally, they get the similar part between the previous one. And this is for the okay. Yes, the similar things. This kind of big graph. Those kind of big graphs. So they're using this alpha distribution, and this is beta, gamma, and theta. Okay. Because for this, for alpha distribution, G and K they're all using the order of 0 that to relate to themselves. Okay. So basically, this is all of our paper. So this paper is kind of using the new proposed module to replace a process of this partially exchangeable network to reach the better performance as approximate Bayes computation. So that's all our brief explanation, and thank you very much, and looking forward for the Monday online presentation with my teammates and with Professor Yu. Okay, thank you.
Okay, hello. Today, let's talk about the information in experiments, specifically the G and K distribution. It's a part of the experiment, and G and K distribution from the experiment showed here. And the result is based on these pictures from when the data set, the difference between both experiments are the same, but the G and K distribution are more specifically on showing the MLP and the compare with the stimulated. For this, using this G and K distribution finds that actually the small data sets didn't have the very vastly better performance. Okay, let's analyze it specifically. It's basically the G and K distribution defined by its quantitative function for 4 parameters, which is based on the MLP and the P0, as you can also see in this chart here. I think there are 5 different methods. Yeah, compare of them is constructing the summary statistics. Still basic on the ABC, which is handpicked summary statistics in this one, which you can see is based on the SY, based on these functions is P20, 40, 60, and 80. I think this is a reference and it's not really important. The most important things is PI is ice, and the from here is the 2, 3, and 4, which is the MLP small, large, and the network with a progressing step, denoted the MLP pre. And the probability density function for G and K distribution can approximate the finite difference, as you can see here. It also references this one, but the GK and R package here, I don't think is shown clearly in this chart. But the next part, which is which is from here, the evaluate part, which combines the interface produced using summaries constructed from 5 methods. That one, I think, is the most important part in this G and K distribution experiments. As you can see here, the ABC interface repeats over 100 independent data sets. It also shows in this. Experiment. It all use over 100 repetitions, and it's in fact that the PN0 requires 10 times less training data than MLP pre. is based on this line, as you can also see here. And based on this evaluation calculation, is also showed in this code. It's also get this code here, and you can see the PN2 and PN0 is always the about 10 distribution lower than the MLP and small and the large. And in this formal picture, and it's based on simulated Western distance, the handpicked is on the upper part, but in the code it's running the handpicked is in the lower part, but it still limit Western distance. And the number of objects in training data are still the same. So as you can see, the MLP pre and the only difference is MLP pre here and here in these two charts. That's the biggest difference. You can also see here 10 times less training than MLP pre to achieve the same interference accuracy. However, all methods performed poorly when two field training observations are used, which is MLPs feed with the observations. But if we instead use, this is attention here, instead use and send the imperial distribution function in the spirit, we can obtain considerably better results. In my opinion, the generous poor results, the instead MLP here is the two difference between the charting here and the charting in the code. I think that's the most important one, which you can see these two pictures have the meaning same result, but the showing way is totally different. And I think that's all about the G and K distribution based on my understanding. And thank you.
I will focus my explanation on the alpha stable function. For the characteristic function phi-x for the alpha stable distribution, I want to explain something about it. So from the paper, we know that alpha stable models are a convenient family of heavy-tailed distributions used in a number of applications. Inference is challenging, since for distributions in this family, there's no closed form expression for the density function. The most common parametrization of these distributions is in terms of a parameter theta. So it equals to alpha, beta, gamma, and delta, where alpha is a parameter controlling tail behavior. Beta controls skewness. Gamma is a scale parameter, and delta is a location parameter. Also, from these supplementary materials, we got this sine function. It is a special continuous time function. It's a jump from 0 to 1 process, and it returns an integer variable that indicates the sign of the argument. Syntax sine x. The t argument is any valid numeric expression. Sine returns 1 if number is greater than 0. Equals 0 returns 0, and less than 0 returns minus 1. From the paper, we know that we need to calculate this RMSE value. So let's look at how it works. According to some independent Gaussian priors and some defined constant values, we evaluate the different methods by comparing the root mean square errors. between ground truth parameter values and the ABC posterior means. We can also see the RMSE formula is just similar to the general square arrow function. So the smaller of this value means the more accuracy of this model. From the table, we know that PN0 has the best result, and it performs better than these three types of MLP models and hand-picked one.